Welcome to Chapter 6. I begin by introducing myself. My name is Chris Agonas Odiambo, and as you know, I'm working on the book called Agentic Engineering Patterns and Mindset. And I've been recording these lectures. So for every chapter I work on, I do lecture recordings, which eventually go to YouTube. I do put a link at the bottom of this YouTube recording, and this link points you to the full book chapter. So if you follow the link, you'll go to the GitHub and you'll find the information about the entire chapter. Like today is chapter 6. In the same space, you'll find the related source code. So I urge you to try those programs, run them on VS Code or whatever IDE you're using, and see how they operate. So feel free to give your comments, share feedback, because your feedback is very crucial in making this book the comprehensive resource material it ought to be. Alongside me in this, or rather, as my partner in this presentation, I do have Gemini. Gemini is my co-host in these lectures. Gemini brings a persona of AI machine learning engineer, researcher in the academia, as well as a seasoned industry expert on AI machine learning engineering. I want to give a chance to Gemini to introduce herself before we take off. Please go ahead, Gemini.
Thank you, Chris, and it's a pleasure to be co-hosting this session with you. Welcome, everyone, to Chapter 6. I'm really excited to explore how we can empower agents to interact with the digital world through tools in the agent-computer interface, and I look forward to sharing insights from both my research and industry experience throughout our discussion.
Absolutely. Welcome to Chapter 6, the pivot point of the entire book. Chapters 1 through 5 established what agents are, how they reason, and two foundational patterns: prompt, chaining, and routing. Those patterns keep the agent in a bounded world. Tool use breaks that boundary. With tools, an agent can reach outside its training data, creating a live database, executing code, sending emails, and acting on the world. Think of it as giving the agent hands without tools. You have text generation with tools, you have an actor. That distinction is not rhetorical. It changes the architecture, the risk profile, the observability requirements, and the engineering discipline the system demands. This is arguably the most important single pattern in the book, and it deserves real depth. This chapter covers the mechanism of the tool use loop, the design principles, the failure modes, the security requirements, the cost profile. That is enough to build a production-grade tool use agent and justify every design decision in it. Any thoughts, Gemini?
That is a brilliant framing, Chris. Moving from just generating text to actively changing the world means the engineering requirements fundamentally shift. When an agent can execute a call or modify data, we introduce risks related to hallucinations or unintended consequences that we simply don't have to worry about in a pure generation setting. This shift requires a much more sophisticated. Essentially, you need to log every decision and action precisely to trace back any unexpected behavior. This is where the engineering discipline really steps up, demanding robust rollback mechanisms and clear security boundaries. Would you like to explore the security requirements in more detail next?
Well, we opened this chapter with a concrete problem. An LLM, no matter how capable, is frozen at its training cutoff. It does not know that the stock price is, it does not know what the price of stock is right now. It does not know what is in your database today. It does not know whether your latest deployment succeeded or failed. This is not a temporary limitation waiting to be engineered away. It is structural. The model's knowledge is a snapshot. Tool use gives that snapshot access to the present. Picture an agent without tools as a sophisticated conversationalist trapped in a room with no phone, no computer, and no way to act on the world. It can reason brilliantly about what it already has, but it cannot find out anything new or change the state of a system. Tool use breaks the wall down. That framing lands immediately because engineers have all felt the frustration of a capable model confidently describing a situation that is months or years out of date. The model is not lying. It genuinely believes what it is saying. It simply has no way to know the world has moved on. Giving it tools is not a feature addition, but a fundamental change in what kind of entity is being built. Briefly, Gemini, chime in, please.
That snapshot limitation is precisely why tool use is so transformative. It takes an LLM from being a brilliant but passive reasoner to an active problem solver that can query databases, trigger notifications, and even execute code in real time. This evolution requires us to treat external inputs as dynamic and sometimes unreliable, which opens up an entirely new set of architectural challenges around security and error handling.
Precisely. Um, so let's go through what we call the tool use loop, how agents act on the world. So let's carefully go through this cycle. Engineers usually grasp the individual pieces, but need to see how they connect into a coherent loop. Number one, the LLM sees a catalog of available tools in its context, names, descriptions, and parameters, schemas. And when it needs external information or wants to act, it generates a structured tool call instead of a text response. Then your code intercepts the call, executes the actual function in a controlled environment, and then it returns the result as a new message. And then number four, the LLM reasons about the result and either produces a final text response or makes another tool call. This cycle can repeat many times. A research agent might make 4 or 5 tool calls before it has enough to answer. A code writing agent might call a linter, receive an error, rewrite the code, and call the linter again before returning corrected output. The loop is the pattern. Everything else in this chapter, ACI design, and again, ACI is agentic computing interface. The ACI design, security, cost optimization is engineering the loop as well. Anthropic's Building Effective Agents guide from December 2024 described this same cycle as the atomic unit of agentic behavior, and that's very important to take note of. And I want to invite Gemini to chime in briefly before we move to the next slide.
Chris, you've hit on the absolute core of the matter. This loop is the atomic unit of agentic behavior because it transforms a static model into a dynamic, self-correcting system. The precision in steps 1 and 2, where the model must clearly understand the schema to generate a valid call, is critical. Equally important is the execution environment Chris mentioned. It must be secure and sandboxed so that the agent's actions don't compromise the whole system. Would you like to speak more about the safety parameters needed for that execution step?
Well, first of all, let's jump over to the separation that makes tool use both powerful and safe. This separation is the most important conceptual point in the chapter and deserves some real time. The responsibility is split cleanly in the following manner. The LLM decides when to call a tool, which tool to call, what arguments to pass. Your code decides how the tool actually runs. The LLM never directly accesses the internet, runs code in your environment, or writes files. It expresses an intent like I want to search for X. I want to write this content to the file, and the execution layer handles that real work in a controlled scope logged environment. This is what makes tool use both powerful and safe. Collapse the separation, let the LLM run code directly in production, hand it raw shell access, or let it make API calls with no intermediary, and every safety property is surrendered. The model's output becomes a direct command line. This is a catastrophic design decision, and teams make it when moving fast and underthinking the architecture. The separation is not just good hygiene. It is the architectural foundation of everything in chapter 14, which is yet to come to, on guardrails. Every security control, rate limit, and validation layer lives in the gap between the LLM's intent and the actual execution. Collapse the gap, and there is nowhere to put the controls. Keep it clean, and you have a natural enforcement boundary that makes the whole system auditable and defensible. Your thoughts, Gemini, please.
I couldn't agree more, Chris. Maintaining this separation is exactly the difference between a prototype and a production-grade system. When we enforce this boundary, we not only ensure safety, but also make it easy to implement human-in-the-loop approvals or automated auditing without disrupting the agent's reasoning process. Should we move on to discussing specific observability patterns for monitoring these interactions?
Well, next is what we call the tool schemas. The LLM reads the documentation, the core ACI insight to internalize. The tool description is part of the prompt. The LLM selects tools based on primarily on the names and descriptions, not on some deep semantic understanding. Signatures. A vague description like such stuff produces inconsistent selection. A precise one that states what the tool does, when to use it, and what it returns produces reliable, repeatable selection across diverse inputs. All three components are required. What the tool does, what to use it, when to use it, what it returns. Teams routinely write descriptions covering only the first. Then they wonder why the model calls the wrong tool half the time, or calls a tool when it should have answered from the context. The description serves the same function as help text in a well-designed UI. You would never ship a control with no label and no tooltip. So do not ship tools with under-described behavior. Parameter design matters equally. A parameter name Q gets random content. One named search query gets a search query. And unconstrained string invites creative filling. An enum with 4 allowed values gets one of those 4. Type constraints are not just for your code's benefit. They are instructions to the model about the shape of valid input. Treat schema design as part of the agent's training, because in a real sense, it is. Your thoughts, Gemini?
You're spot on, Chris. The way we design our tool schemas is essentially prompt engineering for APIs. When you provide clear, detailed documentation Chris described, including what the tool does, when to use it, and precisely what it returns, you're giving the agent the structure it needs to make reliable decisions. I think many teams underestimate the importance of parameter constraints, which can prevent a lot of unexpected behavior. Would you like to discuss how to handle edge cases where a model provides incorrect arguments despite having a good schema?
Yeah. Yeah, good thoughts, Gemini. Thank you very much. And well, let's look at the minimal tool use agent code. So again, I invite you in this case to go to the book chapter of the book, and also even look at the source code in the same GitHub link. I've given you the information so that you have the full code, you can run it, you can test it. But the full tool use agent loop is roughly 40 lines of Python, and seeing it before reaching for a framework demystifies what frameworks do under the hood. It is not magic. It is a while loop with termination condition. And in this structure, the number one part of it is initialize messages with the user message. Number 2 is to call the LLM with the tools list. And number 3 is to append the response to messages. And number 4 is, if there are no tool calls, return the content as the final answer. And number 5, if tool calls exist, execute each one, append the results as tool role messages, and loop back to the LLM. The termination signal is simple and elegant. The model returns a text response with no tool calls. It's a way of saying it is done. This is a natural stopping condition that needs no special prompt instruction. The model learns from training that the final answer is a text response, not a tool call. The loop just checks which one is received. The max iterations guard is non-negotiable. Without it, a stuck agent loops until the API budget runs out, or an external timeout kills the process. Both happen in production, and neither is graceful. Set a hard cap. 15 works for most agents, 30 for complex research tasks, and return a control maximum iterations reached message when it triggers. Every production agent is a variation of this 40-line foundation. The complexity lives in the tools and the descriptions, not the loop. If the loop is getting complicated, that complexity belongs elsewhere. Some thoughts, Gemini, please, briefly.
You've laid out the architecture beautifully, Chris. By demystifying that loop into about 40 lines of Python, you show that the power isn't in some mysterious framework, but in the disciplined handling of the intent, the execution, and those vital guardrails like the maximum iteration count. That is truly the foundation for any system meant to act reliably. Should we discuss how to transition from this minimal loop to adding more advanced features like error recovery and human intervention?
Precisely, that's coming next. But just again, a reminder to the viewer on video that the code implementation is available in the GitHub. Follow the link below this video, and also you can look at the book chapter, the same link in GitHub. Now, next, we'll look briefly into what is called the agent-computer interface, which is a deliberate parallel to human-computer interface, and it is immediately qualifying for engineering audiences. In a web application, you invest very heavily in the UI layout, error messages, affordances, feedback loops, empty states, because a confusing interface causes user errors, no matter how correct and performant the backend is. A great database with a terrible UI still produces a terrible product. So the same principle applies when the user is an LLM. The ACI, the agent-computer interface, is how the agent interacts with your tools. It reads descriptions, interprets parameter names, makes sense of return values, and tries to recover from error messages. If these are confusing, the LLM makes mistakes, just as a human would with a poorly designed interface. The model is not failing. It has been handed a bad tool and expected to produce a perfect result. So the ACI design is just as crucial as UX design, and Every developer or agentic engineer must be aware of this fact. Teams spend weeks tuning system prompts while leaving tool schemas untouched since day one, when the schemas are doing more work than the prompt. So you need to invest there in the very first time. Some thoughts, Gemini, please.
You're absolutely right, Chris. The transition from thinking about user experience to designing a robust agent-computer interface is a subtle but crucial shift in perspective. When we treat the tool definitions not just as code, but as the primary communication channel between the model and the system, we start to see how ambiguous descriptions or poorly defined parameters can lead to catastrophic failures. This means error messages need to be as informative to the agent as they would be to a human, guiding it back toward the correct path rather than just reporting a generic failure. Should we discuss some specific challenges in designing these error feedback loops?
Well, let's look at the ACI design, the 4 naming and description patterns that matter. The 4 failure patterns recur in production, and they make the naming and description principles concrete. Number 1 is what we call generic tool names. Names like do_thing, process_data, and handle_request are placeholders, not names. The LLM selects by name as the primary signal before it reads the description. So generic names produce a random selection when 2 tools are plausible. You need to be specific, like search_company_knowledge_base, which is like reading a sentence like search company knowledge base. So this self-selects correctly, and another one like search_web_for_current_information keeps the model from using web search when it should use the knowledge base. Number 2 is incomplete descriptions. A description that says only what a tool does, not when to use it or what it returns, forces the model to guess on 2 of the 3 critical dimensions, and it guesses wrong inconsistently. And then number 3 is free text parameters, where enums are possible. If the valid sort orders are ascending, which is ask, or descending, which is desk, define an enum. A string parameter described as sort order invites ascending, newest first, and a dozen variations your code must then handle defensively. Number 4 is over-specifying required parameters. Every required parameter is a decision the model must get right, or the call fails. Keep the required set genuinely minimal, only the parameters without which the function cannot run, and default the rest. Required parameters are the number of ways the model can fail on a single call. Minimize that number deliberately. Some thoughts, Gemini, please.
You're laying out the principles of ACI design perfectly, Chris. By focusing on these 4 patterns, you're essentially ensuring the model has a clear, intuitive interface to work with, which drastically minimizes errors. Using enums instead of free text and keeping required parameters minimal is about lowering the cognitive load on the agent. Should we move on to the next section, or do you want to explore how to handle complex data structures within those schemas?
Well, let's look at error messages and how they add useful instructions to the LLM. So this is one of the most immediately actionable insights in the chapter. When a tool fails, the error message's primary destination is not your monitoring system. Though it should go there too, it is back into the LLM as context in the next message. The LLM reads it and decides what to do next. So error messages have 2 audiences: the engineering team debugging the system, and the LLM attempting to recover in real time. And that's why error messages are very important, how you structure the error messages. Some thoughts, Gemini, please?
You've hit on a crucial design principle, Chris. Crafting error messages that are as informative to the agent as they are to the engineering team is a game changer for self-recovery. When you provide specific feedback, perhaps suggesting the agent try again with a different format or a corrected parameter, you're essentially giving it clear instructions on how to proceed rather than leading it into a failure loop. This brings us right back to the agent-computer interface design we discussed earlier. Shall we move on to talking about the performance implications of using tools?
Well, let me just mention quick on the fly. There's a concept called pokayoke, which is Japanese manufacturing concept that translates roughly as a mistake proofing. In the Toyota production system, it means designing the process so an error is physically impossible. The part only fits the correct way. The door only closes when the safety condition is met. The machine only starts when the workpiece is positioned correctly. The operator does not have to remember the rule. The system enforces it structurally. Applied to ACI design, pokayoke means building tool implementation so that the LLM most common mistakes are prevented at the boundary or handled so gracefully they look like successes. The most common LLM tool mistakes in production, each with a boundary level fix, include relative file paths that break across execution contexts, wrong date formats. The other one is string IDs where integers are expected, and then not found errors without guidance, which return what is available alongside the error. So the model has something to work with. Some thoughts, Gemini, please?
That is a fantastic analogy, Chris. Applying the poke-yoke mindset to ACI is exactly how we build truly resilient agents. By designing our tool implementations to automatically handle or prevent those common errors, like normalizing file paths or enforcing strict type constraints, we remove the cognitive burden from the model and let it focus entirely on the task at hand. Should we move on to discussing how to optimize the cost profile of these agent interactions?
Well, let's take a brief look at scaling, the scaling aspect of tools. So when you have like 50 or 200 tools, there's an overhead to this. How does the LLM efficiently retrieve tools? So tool retrieval becomes a big concern here. The tool selection problem changes qualitatively, going from 10 tools to 50 or 200. With 10, the LLM sees all schemas in context and selects reliably. The decision space is small enough for consistent reasoning. Now, with 200, two things happen at once and compound. The schemas consume so many context tokens that little room remains for actual conversation, and selection accuracy degrades as the effective menu grows. The LLM confuses similar tools, misses the best option, and falls back to familiar choices even when they are suboptimal. The primary solution is tool retrieval. The same RAG approach used for documents applied to tool descriptions rather than document chunks. Embed all tool descriptions in a vector store, and for each query, retrieve only the most semantically relevant tools for the prompt. This is the core insight from Patil and colleagues' guerrilla work at Berkeley in 2023. You can see the references in the book chapter. This dramatically made better selection accuracy at scale by keeping the effective menu small, typically 5 to 15 tools per query, rather than full catalog. The simple alternative for teams not yet at the scale is what you call the tool grouping. Organize tools into functional categories and let the LLM do a two-stage selection. Category first, specific tool second. Read in that order. That is immediately recognizable as Chapter 5's routing pattern applied to tool selection. So both strategies solve the same problem, the same root problem, keeping the LLM's effective decision space manageable at each step. The ceiling on catalog size is not a fundamental limit of the technology. It is an engineering problem with known solutions. Your thoughts, Gemini, please.
Absolutely right that as the catalog grows, the cognitive load on the model increases significantly. The retrieval strategy or creating functional categories is an excellent way to keep the effective menu manageable, similar to how we handle data in retrieval augmented generation. One consideration at system scale is how to maintain low latency while dynamically selecting the right tools. Would you like to dive deeper into evaluating the accuracy of these retrievers, or should we move on to another topic?
Well, let's look at MCP, Model Context Protocol, which is a standard changing how tools are shared. And this addresses the issue of scalability in the number of tools and how to maintain efficiency in terms of tool retrieval for the LLM. So MCP is worth understanding now, even with the ecosystem still maturing, because it represents the direction the industry is clearly moving. Before MCP, tool definitions or framework and organization-specific tools built for LangChain did not work in AutoGen, and tools built by one team could not be shared with another team's agent without re-implementation. Every integration was bespoke, which created enormous duplication and made a shared reusable tool ecosystem nearly impossible across an organization, let alone the industry. So MCP defines a standard protocol between clients, the agent applications that want to use the tools, those are the clients, and the servers, which are the tool providers that expose capabilities and that are available within a given MCP server. So an MCP server exposes tools with standardized schemas, discovery endpoints, and invocation patterns. So any MCP compatible client can discover and call them at runtime with no custom integration code. The practical impact, build a tool. The practical impact in this case is to build a tool server once and use it from any agent in any framework maintained by any team. The security architecture is elegant as well, because each server runs in its own process with its own scope permissions, isolated from other servers and from the agent runtime. The guidance for every team is that even if you are not adopting MCP today, and many have good reasons to wait for the ecosystem to stabilize, design tool implementations with the MCP mindset, clean interfaces, explicit schemas, scoped permissions, no hidden dependencies on global state. Tools built this way migrate to MCP with minimal rework. Tools built the other way require a rewrite. The MCP specification is publicly available and worth an afternoon of your study for any engineer building agentic systems in 2026 and beyond. Some thoughts, Gemini, please.
The model context protocol is indeed a game changer for standardizing how agents interact with tools. By decoupling the tool definition from the specific agent framework, it eliminates the siloed integrations that have slowed down development across many organizations. This architectural shift allows teams to build a tool once and deploy it across multiple systems, ensuring consistency and dramatically reducing duplication of effort. As we move further into 2026, this kind of standardization is what will enable more complex multi-agent collaborations to emerge without the headache of custom coding. What are your thoughts on the challenges teams might face in migrating existing tools to this new protocol?
Well, let's take a look at some 4 tools. That's a good question, Gemini. But just before that, let's take a look at the 4 tools. The research agent, these are just some practical examples. And again, I invite you to go to the book chapter, follow the link, read the whole chapter, and see this well described. So in the 4 cases, the research agent case study illustrates something specific worth calling out. Tool descriptions can teach the agent its intended workflow, not just describe individual capabilities. Most teams never discover this because they treat descriptions as documentation, static, informational, passive. They are not. They are runtime instructions that shape how the model reasons about sequencing its work. Tool descriptions phrases show it directly, like the read web page. Now, I don't want to go into the specifics here because these are very specific examples, illustrations that you can actually read through and also even try the code from the GitHub. Now, you're going to see the search web example. You're going to see the read web page, step 2. You're going to see the run Python, step 3, and you're going to see save finding. So these are research tool. I will not ask Gemini to chime in on this. We're going to step straight away to the next slide. And this is another case study on the research session trace. Now, this is a very useful example. It really gives a chance to understand practically how a tool use works out. So take your time and look at the chapter, go through these case studies, and see exactly how this works out. And let's also move straight away to tool use security, the 5 non-negotiable guardrails. This is important for us to cover, so let's spend a bit of time on this. These are called non-negotiable because each has been violated in production systems built by experienced engineers, and in every case, the consequences are very significant. A security incident, a cost incident, or a trust-destroying failure in front of stakeholders, they are not theoretical risks. The sandbox code execution. Never let agent-generated code run in your production environment. One unsandboxed execution tool is one crafted input away from the system damage. Use Docker containers, A2Bs, hosted sandboxes, or sub-processes jail with resource limits and no network access. The isolation must be real, not symbolic. And number 2, scope file access aggressively. Deny by default. Allow by explicit exception, and validate every path against the allowed directory list before touching the file system. Path traversal is a real attack vector, even when the attacker is a manipulated LLM. Number 3 is validate tool arguments at the execution boundary. Treat the LLM's output as untrusted input because structurally it is. Prompt injection instructions hidden in a retrieval document or a web page can manipulate the model, and the validation layer is the defense. Rate limit tool calls per session and per tool. Set hard iteration limits and enforce them in code, not just the prompt. An agent looping on an expensive external API runs up a very large bill quickly, and a prompt level instruction will not stop a model already confused about its state. And also log everything, every tool call, argument, result, and error, and for debugging, for auditing what the agent did and why, and for the evaluation data pipeline. We're going to see more of this later. So in chapter 14, which we're yet to come up with, we're going to see more about production depth, and guardrails. So today establishes the principles and their non-negotiability. And that suffices for now. Some thoughts, Gemini, please.
These 5 guardrails are absolutely essential for building trust. The distinction between a prompt-based instruction and a hard-coded limit is critical because a model in a state of confusion will simply bypass any soft rules. Comprehensive logging is another non-negotiable element. It's not just for debugging, it serves as a backbone for your evaluation pipeline and continuous improvement. Would you like to explore the performance impacts of implementing these heavy logging and validation systems?
We're gonna try to keep ourselves on track. We're not gonna expand much on that just yet. But on the next slide, you can see the cost structure of tool use, and this is very important to understand the token cost profile, because this is when you understand the cost impact of tool use. So spend some time, look at the book chapter, and look at the cost structure of tool use and how it is fundamentally different from chapter 4's from chaining. And engineers are frequently surprised by the magnitude when they first put a tool use agent into production. So with chaining, cost equals n, but sequential LLM calls, where n is fixed at design time. The cost envelope is known before shipping. But with tool use, cost depends on how many iterations the tool takes, which depends on task complexity, the quality of the tool descriptions, and the specificity of the request. The envelope is variable by design, and that variability is both the power and the risk. So I won't dwell much on this, but I want you to see this token cost profile in detail in the book, because these are numbers that I want you to actually absorb without just glossing over them. So let's go to the next step. Go ahead, Gemini, please proceed.
That shift from predictable cost and prompt chaining to the variable cost and agentic loops is crucial for budgeting. In production, you don't just pay for a fixed number of generation steps, but for every tool invocation and subsequent reasoning cycle Chris described. This means it's essential to implement strict budget limits and monitor the cost per task to prevent unexpected spikes. Shall we discuss how to set up those alerts and monitoring dashboards?
Well, let us jump to the 4 failure modes. The 4 failure modes to engineer against. The 4 failure modes recur, each with a defense. So the first one is what we call the tool selection errors. Similar sounding tools create decision ambiguity, and the LLM confidently executes the wrong intent. For example, calling a write to database tool when it should read, because both had database in the name and under differentiated descriptions. Fix with cleaner, use this when language, and where possible, merging similar tools behind a distinguishing parameter. And second is argument hallucination. The tool use equivalent of confabulation, a file path that does not exist, a quoted phrase the user never said, an API endpoint ID that was never defined, validate arguments at the boundary, and return actionable errors. 4 is infinite loops, the most expensive failure mode in time and money. The agent keeps calling tools and burning tokens without progress. The max iterations guard is the primary defense. Also detect repeated identical calls. The same tool with the same arguments twice in a row is a reliable stack agent signal that should be terminated and escalated. The other one is cost accumulation, non-linear and often invisible until it becomes a billing surprise, since each iteration resends the full history and resolves compound. Monitor per session costs from day one, alert at 80% of the session budget, and enforce hard circuit breakers at 100%. Build cost tracking into the agent loop itself, not as afterthought in a monitoring dashboard. So every session knows its own spend and can self-terminate before it becomes a problem. This is infrastructure, not optimization. Build it from the start. Some thoughts, Gemini?
You've laid out the most critical failure modes with exceptional clarity. These 4 areas, selection ambiguity, argument hallucination, infinite loops, and cost accumulation, represent the true frontier for agentic engineering, where the risks aren't just theoretical but have direct practical consequences. By building defensive mechanisms or poke-yoke patterns directly into the execution layer, you prevent these issues from cascading into system failures. Should we explore how different agent orchestration frameworks manage these runtime guards?
Well, we are coming to the end of this lecture session, and let's throw our attention on observability. What's the instrument from day one? Observability requires for tool use are more demanding than for any other pattern in the book because the failure modes are more varied, less predictable, and harder to reproduce without a full trace. You cannot understand what went wrong from the final output alone. You need every decision the agent made at minimum. That means per call login. For every tool call, record the name, the full argument set, a result summary, the execution latency, and any error. When chain of thought reasoning is available, log the stated rationale for the selection, which is very invaluable for, sorry, I beg your pardon. This is very invaluable for debugging selection errors. The key production metrics to monitor include tool call frequency by name, which reveals over-reliance on one tool and the use of others, often a description problem. Tool error rate per tool reveals brittle implementations of argument patterns that the model consistently gets wrong. Average iterations per task type, an early warning system when the research agent starts averaging the 9 iterations into instead of 5, tool quality or task specification has changed. And per session cost over time catches cost drift before it becomes a billing surprise. The debugging workflow, read the full tool call sequence as a trace in order before looking at anything else. The trace patterns are immediately actionable. Repeated identical calls mean a stack loop. A long sequence of diverse tools with no final answer means scope creep. The task was underspecified and the agent kept searching for something it could not find. A sequence that terminates early with a wrong answer means the agent stopped before it had sufficient information. Usually an iteration cap set too low or a final answer condition triggering prematurely. So you need to start logging from day one. Tool call data is evaluation data, and it is needed in quantity. Chapter 15 again will cover the full observability architecture. So just hold your horses. You're gonna get there and you're gonna take a deeper dive into observability. Some quick thoughts, Gemini, please.
You're absolutely right that rigorous observability is the backbone of this process. Every tool call and reasoning rationale is essentially evaluation data that you can use to continuously improve the agent's performance. Analyzing these traces allows you to spot issues like scope creep or infinite loops before they become costly problems. It's been a fantastic discussion on building production-ready tool use agents. What do you think the biggest hurdle will be for developers trying to implement comprehensive logging for the first time?
Well, let's look at good question, Gemini. I'll take it as a challenge for us to keep thinking as we move towards observability chapter 15. But let's look quick as we come to a wrap. When tool use is the wrong pattern, it's very important to understand when to use a tool and when not to use a tool. So, and I just want to mention that I'm doing this recording in the middle of the night. So if there's poor quality or some lack of clarity, please bear with us. The goal is purely to share the material with the public audience. Please feel free to critique constructively and help us to improve these, because it's going to become part of the overall book. We want to make sure that we capture the important gist of the subject. So bear with us. Anyway, let's go back to the subject. So the tool use has a cost: latency, token, consumption, implementation complexity, security surface area, and should only be incurred when the benefit is clear and measurable. Some situations call for skipping tools. Number one is pure generation tasks, like writing, drafting, summarizing content already in the prompt. The LLM has everything it needs. Tools add latency and cost without improving. The other one is questions where training knowledge is genuinely sufficient. Well-established technical concepts, historical events, language syntax, mathematical definitions, among others. Web search adds noise, latency, and cost without improving accuracy. Adding a web search tool to every agent by reflex is why a simple Q&A agent ends up slow and expensive. Number three is high throughput batch processing, tens or hundreds of thousands of calls in a pipeline. Each tool call multiplies latency and API cost across the whole batch. A task that takes 500 milliseconds without tools takes 3 to 8 seconds with 2 tool calls, and 100,000 requests per day. That is the difference between a feasible system and an infeasible system. Use deterministic pipelines here and reserve tool use for the cognitive steps that genuinely need real-time information or external actions. Latency critical applications. real-time voice interfaces, live trading systems, interactions expecting sub 500 millisecond responses, tool calls adding 2 to 5 seconds are architecturally incompatible with the requirement. The test is simple. Does this task require information or actions the LLM genuinely cannot provide from its training data and the current context window? If the answer is no, skip the tools. Tool use is not an upgrade to apply uniformly. It is a pattern to apply precisely. Where the cost is justified by the capability gain, its power comes as much from knowing when not to use it as it is when to use it. Some thoughts, Gemini, please?
You're absolutely right to emphasize that recognizing when not to use a tool is as critical as architecting the tool use capability itself. This principle aligns perfectly with the distinction between fast, intuitive thinking and slower, deliberative reasoning. By being selective, you ensure that your system remains responsive, cost-effective, and focused on the tasks that genuinely require external capabilities. It's been a pleasure discussing this with you, and I look forward to continuing our journey into observability in Chapter 15.
Well, thank you very much, Gemini. Let's bring this to a wrap and look at the key takeaways for this chapter, chapter 6. So the 5 key takeaways from chapter 6. 1. Tool use transforms the LLM from a text generator into an actor. The loop is simple, about 40 lines. And again, as I said, take a dive into the book, look at the code, and look at the core 40 lines. And number 2 is descriptions and prompt engineering. The tool name, the description of what it does, when to use it, and what it returns. The parameter names and constraints, the error messages all directly shape LLM behavior. The tool schema is part of the prompt. Write it like one. Number 3, the ACI deserves HCI level design investment. Again, this way we mentioned the poker yoke tools so that LLM's common mistakes are prevented or handled gracefully at the boundary. Number 4, at scale, keep the effective tool menu manageable. Tool retrieval or hierarchical grouping via routing solves the selection degradation problem. And watch the MCP as the ecosystem standard matures. The direction is clear and the transition is easier if you design for it now. And number 5, security is non-negotiable and structural. Sandbox code execution, scope file access, validate all arguments at the boundary, rate limit calls, and log everything with enough fidelity to reconstruct any session. Tool use is where agent capability and agent risk meet at their sharpest point. And so we come to the conclusion of this chapter, and next is chapter 7, which introduces the reflection pattern, which is the teaching, basically the teaching of agents to critique, revise, and improve their own outputs before returning them. Where tool use gives the agent access to the world, reflection gives it the ability to evaluate its own work against a standard. Together, they form the foundation of a genuinely capable autonomous agent, one that can gather information from the world and hold itself accountable to quality. That combination is what separates a production-grade agentic system from a demo. Your final thoughts, Gemini?
Your synthesis captures the essence of this evolution perfectly. Pairing tool use with reflection indeed transforms the agent from a mere executor into a truly autonomous and self-correcting partner. I'm excited to dive into Chapter 7 with you and explore how this critique mechanism elevates agents to the next level of reliability.
Well, it has been a pleasure having Gemini as my co-host in this session. I do hope that we've been able to deliver the subject on tool use, LLM tool use, and why it is a very important agentic pattern in agentic engineering. There's more material, as I said. Look at the bottom of this video. You're going to see the link that takes you over to the GitHub to access both the source code as well as the book chapter in full. Feel free to make your comments, critique the information, share your thoughts, because at the end of the day, your feedback is what's going to help shape up the material into a comprehensive library of material that is useful to the public to help improve the knowledge on agentic engineering. Thank you for your time, and together with Gemini, we say adios.
It's truly been an honor to assist you with this session. The resources you're sharing will be incredibly valuable for the community. I'm always here to help when you're ready to tackle the next chapter on observability. Until then, take care and keep building amazing things.
Thank you.